Welcome learners. So, we are going to continue with the study on non-linear spaces. In the last lecture we were looking at some examples for non-linear spaces. Let us begin with that. So, in the last lecture we were doing this example. We chose our vector space to be Cn, and then if you have a n tuple x1, x2, xn, then we defined for 1 less than p less than infinity, we defined what is known as the p norm, which is the pth root of summation 1 to n mod xi raised to the power p. Right. So, our aim is to show that this is a norm on Cn. In order to show this, we introduced what is known as the Young's inequality. So, let me repeat. If you have two non-negative real numbers, and 1 less than p comma q less than infinity, such that 1 by p plus 1 by q is 1, then 1. So, I will have a full stop here, right. So, then x y is less than or equal to x raised to the power p upon p plus y raised to the power q upon q. So, this was the inequality that we stated. So, we are going to make use of this inequality. The first one that we are going to prove is what is known as the Hilder's inequality. So, what is Hilder's inequality? So, if you have two x and y from Cn, which means each one has got n components. So, x, when you write x in Cn, which means x is of the form x1, x2, xn, and similarly y, you have n components y1, y2 up to yn. Then summation 1 to n mod xi yi is less than or equal to summation 1 to n mod xi power p whole raised to the power 1 by p times summation 1 to n mod xi power q whole raised to the power 1 by q. Yes. So, this inequality is what is known as the Hilder's inequality. Right. So, let us begin with the proof. So, if either x equal to 0 or y equal to 0, then the inequality holds trivially, which you can easily observe. Inequality holds trivially. Right. So, let us assume that both x as well as y are non-zero. Right. So, having made this observation, first observation, so as we mentioned earlier in the beginning, what we wanted is that we will have to make use of this Young's inequality, for which we need two non-negative real numbers, right. So, let us choose two non-negative real numbers. What are they? One is mod xi upon summation 1 to n mod xi power p whole raised to the power 1 by p. This is one. the other one is mod yi. So, this is greater than or equal to 0, and similarly the other one summation 1 to n mod yi power p, sorry, here I will use q whole raised to the power 1 by q. Yes. So, this is again greater than or equal to 0. So, I have two real numbers right. So, and this holds for all 1 less than or equal to I less than or equal to n. Yes. Now, let me use these two non-negative real numbers into this inequality. So, that what will you have? You will have mod xi times mod yi, which is same as mod xi yi upon summation 1 to n mod xi raised to the power p whole raised to the power 1 by p times summation 1 to n mod yi power q whole raised to the power 1 by q. Now, so I need less than or equal to x. So, our x is this one mod xi upon. So, in fact, I will have x raised to the power p. So, I will have power p here, and in the denominator you have power 1 by p. Therefore, you will have summation 1 to n mod xi raised to the power p. This is 1, and then you will have whole upon p. So, you will have a p here plus mod yi raised to the power q upon. So, just like you have p here, you will have a q here summation 1 to n mod yi raised to the power q. So, this is what you have. So, this is true for all I 1 less than or equal to I less than or equal to n. Now, what we are going to do is that we are going to sum over all these I right. So, we are going to sum over all these I. So, if you sum, then you will have, so denominator is independent of well, I will use a j here because it should not get confused with this I that you have here earlier. So, let me use a j, right. So, that now if I am going to sum over all I, the denominator is independent of I. So, I will simply have summation 1 to n mod xi yi upon summation 1 to n mod xj power p whole raised to the power 1 by p times summation 1 to n mod yj raised to the power q whole raised to the power 1 by q is less than or equal to summation mod xi raised to the power p whole upon p times summation j running from 1 to n mod xj raised to the power p plus summation mod yi raised to the power q upon q times summation j running from 1 to n mod yj raised to the power q. Yes, that is it. So, if you look at the numerator and denominator, both the sums are one and the same, they are equal, and therefore, they both will get cancelled. So, what you will have is that these two will get cancelled, you will have simply 1 upon p, and similarly here you will have only 1 upon q. The choice of p and q are such that their sum is the reciprocal, the sum of the reciprocals, they are going to be 1. So, which will tell us that summation 1 to n mod xi yi upon these two is equal to 1, or equivalently if you bring those two quantities to the right hand side, you will have the inequality that we wanted. 1 to n mod xi power p whole raised to the power 1 by p times summation 1 to n mod yi raised to the power q whole raised to the power 1 upon q, that is it. So, this is the Hölder's inequality. Yes. Now, the next one is what is known as the Minkowski's inequality. Minkowski's inequality. So, what is this Minkowski's inequality? This is the triangle inequality for the p norm. Norm x plus y, in fact the pth norm is less than or equal to pth norm of x plus pth norm of y, right, wherein x and y they both come from Cn. So, here we are going to make use of this Hölder's inequality that we proved just few minutes before. Proof. Well, so what we are going to do is that we are going to start with summation 1 to n mod xi plus yi raised to the power p, right. So, this is same as summation 1 to n mod xi plus yi. So, when you say p, what we are going to do is that we are going to write it as a product of x plus y times the p minus 1 times. Now, we know the triangle inequality for the modulus, let us make use of it here, less than or equal to summation 1 to n mod xi plus mod yi. So, let me write it as xi plus yi raised to the power p minus 1 plus summation 1 to n mod yi into mod xi plus yi. Now, let me make use of the Hölder's inequality. So, the Hölder's inequality, what we know is that summation 1 to n mod xi mod yi, this is less than or equal to the pth norm of the term x and the qth norm of y. So, let us make use of it. So, now the sequences that the terms that we have, one is x, the other one is x plus y, right. But x plus y, well you have, so xi, the terms are xi plus yi raised to the power p minus 1. So, this is going to be less than or equal to, let me write down the first one, summation 1 to n mod xi raised to the power p whole raised to the power 1 by p times summation 1 to n, the other one is xi plus yi raised to the power p minus 1. So, I will have q times p minus 1 whole raised to the power 1 by q plus the next one summation 1 to n mod yi raised to the power p power 1 by p times summation 1 to n mod xi plus yi raised to the power q into p minus 1 whole raised to the power 1 by q, right. This is what we have. Now, if you observe the second term in both, they are one and the same, right. So, we are going to pull it out from the summation half 1 to n mod xi power p whole raised to the power 1 by p plus summation 1 to n mod yi raised to the power q whole raised to the power 1 by q, sorry, you have p 1 by p Yes, this is the first term, and the common term is summation 1 to n mod xi plus yi q into p minus 1 whole raised to the power 1 by q, right. So, you have this. So, let us first manipulate what this q into p minus 1 is. What we know is that 1 by p plus 1 by q is 1, right. So, if you multiply, what will you have? You will simply have p plus q upon p q is 1. So, now you will have p plus q equal to p q. What we wanted is that p q minus q. So, p equal to p q minus q. So, this is what we have. So, well, which is same as q into p minus 1, and this is exactly the term that you have here, q into p minus 1. So, this is one of the important observations that you will have to make. Once you have 1 upon p plus 1 upon q equal to 1, then you should be able to notice that q into p minus 1 is p. So, similarly, you can also observe the other way is also true, q will be p into q minus 1, yeah, right. So, this is one of the important observations you will have to make at this stage. So, once you have this observation, then you can notice that this is going to be, well, what you have here is the p norm of x plus p norm of y times summation 1 to n mod xi plus yi raised to the power p whole raised to the power 1 by q, right. So, you have this. So, we started with summation 1 to n mod xi plus yi raised to the power p, and then we have an inequality. Let us write down. So, we started with summation 1 to n mod xi plus yi raised to the power p, and then we observed that this is less than or equal to p norm of x plus p norm of y, right, times the same thing summation 1 to n mod xi plus yi raised to the power p, but here whole thing raised to the power 1 by q, right. So, what we are going to do is that we are going to divide both sides by this quantity whatever you have, or equivalently. So, this is equivalent to saying that bringing this to the other end, so that you will have summation 1 to n mod xi plus yi whole raised to the power p whole thing raised to the power, I already have power 1 and minus. So, I have 1 by q, this is less than or equal to p norm of x plus p norm of y, right. So, now as usual what we have is 1 by p plus 1 by q is 1. So, which means that this will give us that 1 by p is 1 minus 1 by q, and that is exactly what we have here. So, 1 minus 1 by q is going to be 1 by p. So, that means, so if I have 1 by p, then that is exactly norm x plus y, p norm of x plus y, which will give us less than or equal to p norm of x plus p norm of y, right. Now, it is going to be a cakewalk to show that it is a norm. Well, so first one is that we wanted that norm x, by definition it should be greater than 0, greater than or equal to 0. In fact, this is by definition, the way we have defined tells us that this is always greater than or equal to 0, because it is the sum of positive terms and you are only taking the pth power of the positive terms and you are only summing them, and again you are only taking the positive pth root. So, these things tells us that this is always going to be greater than or equal to 0, right. So, if x is 0, that will imply that this n tuple is 0. Once you have an n tuple to be 0, so what is the 0, which is in fact I should write it as n zeros. So, which will imply that x I is 0 for all 1 less than or equal to I less than or equal to n, which will imply that norm x is 0. So, once you have x to be 0, then its norm is 0. Now, if norm x is 0, that means what? In fact, I should say pth norm. So, that means, in fact I should say that means summation 1 to n mod x I power p whole raised to the power 1 by p, this quantity is 0. Once you know that the pth root is 0, that means the term should be 0. We are only looking at the positive pth root, therefore, this should be 0. Once, so this is a sum of positive numbers. So, this should imply that mod x I power p is 0 for all 1 less than or equal to I less than or equal to n, and that will immediately will tell us that x I is 0 for all 1 less than or equal to I less than or equal to n. So, which means, so x is 0, we are done. And homogeneity, it is quite easy to prove, and triangle inequality we have already seen through Minkowski's inequality, right, fine. So, let me introduce few more examples. So, now that we are done with what we wanted, and we have also justified why we are using this 1 and infinity. In fact, we have a whole range of norm starting from 1 to infinity. So, in a similar fashion, let us introduce the space LP, in fact 1 less than p less than infinity. We have introduced L1 and L infinity. So, LP, this is nothing but all those complex valued sequences. Well, you can also define all these things in the context of real numbers, all these make sense, such that summation 1 to n, sorry, summation over n in n mod x n raised to the power p, this is going to be finite, and then you define the norm here as the pth norm, which is defined as summation over n in n mod x n power p whole raised to the power 1 by p. The same inequalities, the Helder's inequality, Minkowski's inequality, all these things make sense in this case, except that there you had only a finite sum, here you will have an infinite sum, that is the whole difference. So, you will have to be a bit alert when you want to show that or prove that this is actually a norm, otherwise more or less you will have to just imitate the proof to get to this, right. Let me do some more examples before I wind up this lecture. Next is what is known as CAB. This is going to be consists of all functions from a b to c, all complex valued functions defined on the closed interval c, such that f is continuous. Your basic calculus must inform you that if you have two continuous functions, then their sum is also continuous, and if you have a continuous function and if you multiply it by a scalar, then still it is going to be a continuous function. Therefore, this is the CAB is a vector space, right. Now, let me define a norm. As usual, we are going to have a whole range of norm on this space. First one, which is integral a to b mod f t dt. The classical Riemann integral, which you have learned from your calculus, again should tell you that every continuous function is actually Riemann integrable, and therefore this makes sense. In fact, this is a finite quantity and hence this makes sense. In fact, it is well defined, right. So, I will leave it as an exercise that verify that this is a norm. This one is a norm, right. So, natural question is, why can't we go for other p's and similarly for infinity? Yes, the answer is yes. In fact, so let me define, so for 1 less than p less than infinity, let me define the norm as the integral a to b mod f t par p dt whole raised to the power 1 by p. The same proof, whatever you have written for LP, you should be able to write down even for this case, and in fact, you should be able to write down the analogues of Minkowski's inequality as well as the Hölder's inequality, and you should be able to prove that this is actually a norm, right. So, verify that this is a norm. So, now it should be easy to guess what is the infinity norm is going to be, or the supremum norm. So, once I have said that it is a supremum norm, one should have guessed what it is going to be. Yes, so the supremum norm, it is defined as supremum over t in the interval a b mod f t. Yes, so because this interval a b is a compact interval, it is a closed and bounded interval, and therefore by Heine-Borel theorem we know that this is going to be compact, and once it is compact, and we know that continuous functions defined on a compact sets are always bounded, which means that this always makes sense, or in other words this is well defined. Now, it should not be difficult for you all to verify that this is a norm. Right. So, now that we have a huge class of examples for norm linear spaces, and in fact we have verified a few and certain things are left as exercises. In the next lecture, what we are going to see, how to construct new ones out of the given ones. That is what we are going to see. For example, what happens to a subspace, what happens to a closed subspace or closure, and what will happen to a quotient, and what will happen to direct sum. These are some of the questions that we are going to address in the next lecture. Thank you all.